Hello there, this is lecture 17 on section 4.7 on logarithmic differentiation. So one of the things that we did in section 4.7 is talk about the derivative of logs. And something that I pointed out frequently to you is that while logs may not be a comfortable thing for you, it's something that most of us haven't seen in a while, but they have really nice properties so that they make your life a little bit easier. And we're going to take advantage of that in this section. So here's a function that I want you to think about taking its derivative. Okay, so take a look at this sucker. This is has three different pieces, right? So we've got 1, 2, and 3. Each of them is a chain rule. The numerator is a product rule that you can't just multiply out because of the square root. And the denominator means that you've got quotient rule. Okay, so quotient rule, product rule, 3 chain rules. Here's how it would go. Your function 1 is the square root, or x squared plus 2 to the 1/2. Its derivative, using your chain rule, is 1/2 x squared plus 2 to the negative 1/2 times 2x. Function 2 is the x minus 3 to the 4th, and its derivative is 4 times x minus 3 cubed. The derivative in the inside is 1, so I don't need it. Now, I'm not even going to multiply this out yet because what I really need that for is when I do my tops and bottoms for the quotient rule. So everything, the major thing here is that it's being divided. So the top is the x squared plus 2 to the 1/2 times the x minus 3 to the 4th. And its derivative requires the product rule. So I have that set up over here. So 1 prime 2 is going to be 1/2 x squared plus 2 to the negative 1/2 times 2x times the bottom, times 1 prime 2, so that's times x minus 3 to the 4th, plus 2 prime 1, so that's 4 times x minus 3 cubed times x squared plus 2 to the 1/2. That's all the top prime. The bottom then is the x cubed plus 2x minus 1 cubed, and the bottom prime is 3 times x cubed plus 2x minus 1 squared times the derivative of the inside, which is 3x squared plus 2. And this seems like a lot, which it is, right? And then we would finally put all of that together using the quotient rule. So the quotient rule says we want top prime bottom. So top prime is all of that. So that's going to be 1/2 x squared plus 2 to the negative 1/2 times 2x times 2, which was the x minus 3 to the 4th, plus the 4x minus 3 cubed times x squared plus 2 to the 1/2. All of that is the top prime. And I'm going to take all of that and multiply that by the bottom. The bottom is the x cubed plus 2x minus 1 cubed. Oh, geez, I'm running out of space. Let's see if I can move this over a little bit. All right, then, so that's top prime bottom minus bottom prime top. So the bottom prime, this is a little bit better, is 3 times x cubed plus 2x minus 1 squared, 3x squared plus 2, and then times the top, which is the x squared plus 2 to the 1/2 times x minus 3 to the 4th. All of that divided by the bottom squared. Wow, let's see if I can get on the page. And the bottom squared is x cubed plus 2x minus 1 cubed squared. 3 times 2 would be 6. Whew, so I can do it, right? And of course, I'm not going to touch that with simplification. So it's doable is my point. However, it's very messy and complicated. Can we find a better way? The answer here is yes. We're going to utilize our natural logs because if you've heard anything I've said in the last week or so, it's that natural logs turn products into addition and subtraction and quotients into addition and subtraction. So our goal is to eliminate the product in the quotient rule here so that we don't have as much to do. So how can we do that? Well, in order to do that, we've got to get natural logs involved. And the first thing I'm going to do is I'm going to change the f of x to a y equals. So I'm going to make this y equals x squared plus 2 to the 1/2 x minus 3 to the 4th all over x cubed plus 2x minus 1 cubed. Okay, so all I did was change the f of x to a y. And along the side here, I'm just going to keep track of what we're doing so we can kind of develop some steps. So we replace, so number 1, replace f of x equals with y equals. Now those are interchangeable. We use function notation when we usually think about it as a function. We typically use y equals when we think about it as a graph, but they're exactly the same thing. Okay, next, what I'm going to do, if I want to use log rules to help me, I've got to have a logarithm, and I don't right now. So what I'm going to do is I'm going to take the log of both sides. So I'm going to take the natural log of y on the left and the natural log of all of this. Okay, so step 2, take the natural log of both sides. Okay. All right, so we take the natural log of both sides. Now, the whole point of using a natural log is that I can use its properties. So I can split multiplication using addition, I can split division using subtraction, and I can bring down powers. So here's how this is going to happen. The natural log of y on the left stays. I'm not going to mess with that, okay? But here, I have a top divided by a bottom, okay? And I'm going to do this in pieces this first time, and then you can simplify and skip as many steps as you want. So that means I'm splitting with division. That's the natural log of the top minus the natural log of the bottom. So that's the natural log of the x squared plus 2 to the 1/2 times the x minus 3 to the 4th minus the natural log of x cubed plus 2x minus 1. And now I've eliminated a quotient rule, okay? But I'm not done. I can do more. Now I have a natural log of two things being multiplied. I can split that using addition. So this is the same as the natural log of these two added. So natural log of x squared plus 2 to the 1/2 plus the natural log of x minus 3 to the 4th. And then I've got that last term, the natural log of x cubed plus 2x minus 1. There is no rule for the natural log of things being added or subtracted, so I can't pull those arguments apart. But I have one last thing that I can do, and that is dealing with these powers. Actually, I think I lost a power, didn't I? I did. Let me bring that back. Because each of these has a power. And I have a log rule that says when I'm dealing with natural logs, I'm allowed to bring that power down. So this is the same as the natural log of y equals 1/2 the natural log of x squared plus 2 plus 4 times the natural log of x minus 3 minus 3 times the natural log of x cubed plus 2x minus 1. So what did I do? I used in all three of these steps, it took me to use the ln rules to simplify. Okay, so here's what we've done so far. We started out with f of x equals. We replaced our f of x with a y equals. We took the natural log of both sides, and then we used our log rules to split it up, right? To simplify it into things that are not involving products and quotients. And so now when I think about differentiating, now I have 4 terms, both sides, that all involve chain rule, and that's it. And I like chain rule, personally. Okay, the only problem is that this is implicit, so we've got to keep that in mind. Okay, and we'll deal with that at the end. So the next thing we're going to do is we're going to differentiate left to right. So we're going to start with the ln of y. The derivative of ln of y is 1 over y, but it's a y, so we multiply by dy over dx. So that's the implicit part. Okay. Everything on the right is in terms of x's, so I don't have to deal with dy's there. So now let's look at the first term. We have a 1/2, which is a multiplier, so we just leave it. The derivative of the natural log of whatever's there is 1 over whatever's there, in this case, the x squared plus 2. And then we multiply by the derivative of what's inside. In this case, that's a 2x. So we're multiplying by 2x. Plus, we look at this middle term here. And the 4 stays because it's a multiplier. Derivative of natural log is 1 over whatever's there. And then I multiply by the derivative of what's inside. In this case, just 1. Minus 3 for our last term 1 over, for the derivative of the natural log, whatever's in my parentheses, and then multiply by its derivative, so 3x squared plus 2. And that was a whole lot less complicated. So what do we do here? Step 4, we take the derivative from left to right. And in parentheses, I'm going to write, don't forget, it is implicit. Right? On the left, it's a function of y, so watch out for that. Okay, and because it's implicit, the last thing that I have to do is I'm going to get dy dx by itself. The only thing keeping me from having dy dx by itself is this 1 over y, so all I have to do is multiply both sides by y. As I do that, I'm also going to clean this up and make it look pretty. So I'm multiplying by y on both sides, so times y, times y. Okay, so on the left, the 1 over y and the y cancel, and you just get dy over dx. In this first term, the 2 and the 1/2 cancel out, and I have an x on the top and an x squared plus 2 on the bottom. In the second term, I'm just going to multiply across, so 4 times 1 is 4 over x minus 3. And actually, let me write this a little bigger because I feel like we're getting small. So we have x over x squared plus 2 and 4 over x minus 3. In our last term, we have 3 times 3x squared plus 2. So minus 3 times 3x squared plus 2. And that's over 3x squared, x cubed plus 2x minus 1. And I'm multiplying all of that by y because I'm multiplying on both sides. So what did we do? In step 5, we multiply, in this case by y, in most cases by y, to get dy over dx by itself. Okay. And then the very, very, very last thing I'm going to do is this function is now in terms of y, but we started with something all in terms of x's. So I'm going to replace my y with what it's equal to. And what it's equal to is my original function. Okay, so I replace my y with my original function, and that gives me my final answer. So this is going to be dy over dx equals bracket x over x squared plus 2 plus 4 over x minus 3. If you wanted to multiply that 3, you can, or you can leave it factored. Doesn't matter to me. I'm going to go 9x squared plus 6 just because it's less writing. X cubed plus 2x minus 1. And then instead of y, I'm going to write my original function. So it's the square root of x squared plus 2 times x minus 3 to the 4th all over x cubed plus 2x minus 1 cubed. Okay, and so my last step, step 6, we substitute the original function. Let's see if I can spell today. For your y. Okay, and that gives us our final answer. So this is logarithmic differentiation. Okay, we use the power of logarithms to make our derivatives easier. So we start out by replacing your f of x with a y equals so that we can take the natural log of both sides. Then we're going to simplify using our log rule. And once we've done that, we are going to take our derivative from left to right, remembering that we're working with something that's potentially implicit, particularly on the left. And then we just kind of cleaned it up and simplified, and we multiplied both sides by y so that we could solve for dy dx. And then our last step was to substitute y back in so that we had a function all in terms of x. And this is our final answer. So we call this logarithmic differentiation because you're using logs to take derivatives. Okay, they weren't there originally. Please, please don't confuse this with ones where you already have natural logs. Okay? If you already have a natural log, then just use your properties and simplify and go about your business. But if you don't have logs and it's super complicated, then that's an instance where we would use logarithmic differentiation. There are 2 times when we use logarithmic differentiation. We can use logarithmic differentiation on something where it's using multiple rules, right? So the first example was a pretty extreme version. Here's a little bit more of a more simpler one. So 2 chain rules and a quotient rule, you could do it, but you could also do it using logarithmic, okay? And I'll show you that in a second. The other one is in these types of examples where you have a function or you have a variable in the base and a variable in the exponent. We've handled situations where we've had a variable to a number and a number to a variable, but we have not handled something where it's in both. Okay. And so all the rules, I guarantee you somebody's going to write on the test, this is x times x to the x minus 1, because you're bringing down the exponent and subtracting by 1. But that doesn't apply here because the x in the exponent is not a number. Okay, so logarithmic differentiation is our only approach when you have x's in the base and the exponent. And so there's one and there's another. Okay, so let's look at these couple examples. All right, so we're going to go through the process exactly how I described it above. So the first thing that we're going to do is we're going to replace our f of x with y. So this will become y equals. At the same time, I'm going to make it x cubed plus 2 to the 1/2 because that's our standard operating procedure when we're taking derivatives. Okay. Next, I'm going to take the natural log of both sides. So I'll have the natural log of y equals the natural log of whatever's over here. Now that I've got something in terms of natural logs, I can use my properties. So this is a quotient. So I'm going to bring those, split it up using subtraction. So I have the natural log of y equals the natural log of x cubed plus 2 to the 1/2 minus the natural log of x minus 5 to the 4th. I can then also bring down those powers. So we can write it as natural log of y equals 1/2 times the natural log of x cubed plus 2 minus 4 times the natural log of x minus 5. Now I'm ready to go ahead and take my derivative. So I have 1 over y dy dx. There's the implicit part. I leave the 1/2. The derivative of natural log is 1 over whatever's here. And we multiply that by the derivative of the inside, which is the 3x squared. Minus, leave the 4. 1 over whatever's there is the derivative of natural log times the derivative of what's inside, which is just 1. In this next step, I'm going to go ahead and simplify and make those pretty. And I'm going to multiply both sides by y. So I'll make that note here. And that will give me just a plain old dy over dx on the left. And I will have, let's see, 3x squared over 2 times x cubed plus 2 minus 4 over x minus 5. And all of that is times y. And then the last step, I'm going to keep everything I have, only I'm going to replace that y with the function from the original. And my y, if I go all the way back up, my y is the square root of x cubed plus 2 over x minus 5 to the 4th. So I'm going to replace that with my y. So this is the square root of x cubed plus 2 over x minus 5 to the 4th. And that's my final answer. As I mentioned, besides a complicated function with multiple rules, the other time we use this is when we have a variable in the base and a variable in the exponent. So x is in both places. And we're going to use the same procedure. The operating procedure does not change. So I replace my f of x with a y, so y equals x to the x. We take the natural log of both sides. This time we're going to use our logarithm rules just like usual to simplify. And what I can do here is I can take this x and bring it down. So that means I will have the natural log of y equals x times the natural log of x. Okay. Now, I'm going to point this out and be very specific about this because I see this is an issue for people all the time. Every time you use this logarithmic differentiation on something with variables in both places, when you bring down the x, it creates a product rule. Okay, two functions being multiplied together. So when I find this derivative over here, this is my function 1 and this is my function 2. If I'm writing it out, I have function 1 is x and function 1 prime is just 1. Function 2 is the natural log of x and my 2 prime is 1 over x. So when I put this together, the derivative of natural log of y is 1 over y times dy over dx because it's implicit. And then I use my product rule. So 1 prime 2 is just natural log of x plus 2 prime 1 is x times 1 over x. And then while I clean this up, I'm also going to multiply everything by y to move that to the other side. So I will have dy over dx is equal to the natural log of x. The x and the 1 over x will cancel to give me 1, and I'm multiplying that all by y. And the last thing I want to do is replace that y. So I'll have the natural log of x plus 1 times x to the x. And that is my final answer. Okay, so a little bit shorter because they're a little less involved, but you have to remember the product rule. If you don't remember the product rule, then it's all wrong right from there. Let's look at one more example of that type. Here you have the same kind of situation. I have more going on than just x to the x, but I do have an x in both the base and the exponent. First thing I'm going to do, nothing changes here. Start off with y, x to the ln x. So replace my f of x with a y. Take the natural log of both sides. Now, some of you may be saying, hey, I already had a natural log involved there, and I did, but it wasn't in front. So up there, there's nothing for me to simplify. It doesn't have the power it does when I take it out of the function itself. Sorry about that. All right, so now we are allowed to take this power and move it down in front. And that means that we get the natural log of y equals the natural log of x times the natural log of x. Two options here. You can leave it written like that and use product rule, or you could write it as ln of x squared and use chain rule. Your choice on this one. Either way, we're going to differentiate from left to right. So this is 1 over y times dy dx. I'm going chain rule because I don't love product rule either. Chain rule is my favorite. So I'm going to bring down that 2 because I'm taking the derivative. Leave the inside alone, so leave the ln of x. Decrease the exponent by 1, so 2 becomes a 1. Then I multiply by the derivative of what's inside. What's inside is the natural log, and its derivative is 1 over x. And then as I clean this up, the other thing that I'm going to do is multiply both sides by y. So this will become dy over dx. Let me put a y on this side as well. Dy over dx, because the y's cancel. And I get 2 ln x over x times y. And then the last thing that I'm going to do is I'm going to replace that y with the original function, which was x to the ln x. And that's our last example.